In this second part of 11.2, we're going to be talking about the second type of chi-square test that you can run. The second chi-square test is called a test for independence. And the nice thing about the chi-square test for independence is it has the same statistic as homogeneity and goodness of fit. Same way you're calculating degrees of freedom, row minus 1 times column minus 1. And once you get the p-value from that chi-square distribution, you can go ahead and make the same conclusions we've been making if it's less than the alpha, et cetera, et cetera. So most of what this section is about understanding what the chi-square test for independence is and really understanding the distinction between homogeneity and independence. So chi-square tests have to do with a relationship between categorical So we've already talked about when you have more than one population or more than one treatment and you're looking to see if there's a difference between those populations or the treatments in an experiment. The other way that we can use a two-way table has to do when we have a random sample of individuals chosen from a single population, and then we classify them out based on two or more categorical variables. And this is very much like stratifying. So, for example, does one's rating of one's quality of life differ if you're from Canada or the US? Is there an association between heart disease and anger levels? And does the use of social networks depend on age level? These are the kinds of questions that can be answered with a chi-square test for independence. If our goal is to analyze the relationship to the variables, our null hypothesis will be that there is no association between the two categorical variables and the population of interest. And the alternative hypothesis is there is. So just like almost all of the times that we're dealing with a null hypothesis, it's that there isn't, or there isn't a difference, or it's zero. So in this is the same thing, there's no association. That's our null. And if the p-value comes out low enough, then there's statistical evidence that there is an association, and then we go back and look at the follow-up analysis. How are tests for homogeneity and independence the same? For both homogeneity and independence, you're assuming there is no difference or no association. So you're going to calculate the expected counts exactly the same way. Either the way the book talks about it, row total times column total divided by table total, or percent in the column times the sample size. The conditions are the same: random 10%, large counts, all expected counts have to be greater than 5. Data can be displayed in a two-way table. Your chi-square statistic is the sum of all the observed minus expected cells squared divided by expected. Your degrees of freedom, come from row minus 1 times column minus 1, and the test used on the calculator is the chi-squared test. How are they different? We've already dealt with homogeneity. And homogeneity compares two or more populations or two or more treatments in an experiment to see if their distributions are different. But the assumption is always that the distributions are the same, and the expected counts are based on them being the same. And the key thing about homogeneity as opposed to independence is two or more simple random samples are taken from different populations or subjects that are randomly assigned to different treatments. So if the situation starts out with two or more samples, then it's homogeneity. We're looking to see if those two or more samples or two or more treatments are the same. However, the other test, which is independence compares two categorical variables to see if they're associated or independent. The key thing for this is one SRS is taken, and then the subjects are split into groups based on gender or race or geography or age. And when calculating the expected counts and running the test, the assumption is that there is no association, or being a member of one group does not tell you anything about the other variable, and I didn't finish typing that. When we do our null hypotheses for independence, is there's no association between the two, and then the alternative is there is an association. And for homogeneity, we're talking about the distributions for blah and blah are the same, and the distributions for blah and blah are not the same. So we'd be talking about it's still no for both of them, but we're talking about two separate things. One's asking for the distributions being the same, and one's just looking at association or not association. Here we're going to look at an example. Are men and women equally likely to suffer lingering fear from watching scary movies as children? Researchers asked a random sample of 117 college students to write narrative accounts of their exposure to scary movies before the age of 13. More than 1/4 of the students said some of the fright symptoms are still present when they are awake. The following table breaks down these results by gender. Now, which of the two kinds of test is it? This is a test for independence. Is there an association between fear symptoms and gender? And how do we know? It's not a chi-square test for homogeneity. The data were produced using a single random sample of college students who were then classified by gender and whether or not they had lingering fright systems. The chi-square test for homogeneity requires independent random samples from each population. So if they asked only girls and pulled a simple random sample of girls and only boys simple random sample, then you could do homogeneity, but no one's going to collect data that way. The hypotheses in this case is that there is no association between gender and ongoing fright symptoms in the population of college students. And the alternative hypothesis is that there is an association between gender and ongoing fright symptoms in the population of college students. We're talking here, chi-square tests are always a does not equal. It's always a two-tailed type of thought process. So here we have the chi-square test, and they did indeed do a test for independence. The chi-square was a 4. The degrees of freedom was 1 because there's a 2 by 2 table, and then our p-value is 0.045. So when we have run our chi-square test for association with the assumption that there is no association, I want to remind you we calculate our expected counts with that idea. So there were 36 total people that had fright symptoms. 36 total people that had fright symptoms. So we would go ahead and find the percent of people that had fright symptoms, 36 out of 117, and then multiply it by 38 to get that 11.69 expected. So we expected 11.69 of the 38 males to have fright symptoms, but only 7 actually did. And that difference is giving us the biggest addition to that chi-square statistic. So when we go back and do our follow analysis, we want to look at that. Both the female fright symptoms and the male non-fright symptoms also had a fairly decent amount, but the big thing to pay attention is that the biggest one was the fact that men who admit to have lingering fright symptoms account for the largest component of the chi-square statistic. And so far fewer men in the sample admitted to fright symptoms than we would have expected if the null were true. Now, we got to go back and find out that the people decided that they wanted to have an alpha of 0.01. So that means we failed to reject. So gender and ongoing fright symptoms really are independent in the population of interest. There is a 0.045 chance of obtaining a random sample of 117 students that gives a chi-square statistic of 4.028 or higher. Because the p-value 0.045 is greater than our alpha of 0.01, we fail to reject the null. We do not have convincing evidence that there is an association between gender and fright symptoms in the population of college students. If this occurs, where you fail to reject, you do not have to go back and check for the highest component, because there is not a significant result. But this is a really good modeling of how to communicate both the p-value in context, as well as how to phrase it when you are rejecting or failing to reject. So key things. Homogeneity is when you have more than one population that you've taken separate simple random samples for, or you have several different treatments in an experiment. Independence is going to come from data collection of one large sample, after which you disaggregate based on gender or geography or age or something like that.